So, Taylor and MacLaurin series today. This is my favorite part of series. And as I said before, the whole point of using Taylor and MacLaurin is that they can be used to help us solve things like differential equations that involve functions of x and y that make them something called transcendental. And that just means non-algebraic, so e to the x, stuff like that. Give me just 1 second. All right. So, first thing here says consider this function, and it's an exponential, which is e to the x, and I told you that we were going to learn how to solve that. Again, it tells you that e to the x is approximately equal to the sum from n equals 0 to infinity, x to the n over n factorial. So let's prove that this works, and then we can learn how to do it. So the first example says consider e squared and this approximation. So it says approximate e squared to 5 decimal places. So let's just plug that in the calculator. I get that. For part B, it says write out the first 7 terms of this power series. So n equal 1, 2, 3, 4, or 0, 1, 2, 3, 4, 5, 6. That'll give us the first 7. So to do that, I just need to start plugging in n. So it is x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial, and so on. Okay. And really the only ones we can simplify a lot, this first one would just be 1, and this would be x. And if you really wanted, you could write out the factorial numbers here. And remember, those are in your calculator under math, and then it's the probability option. So the fourth one over and then the fourth option down. Part C says, okay, now go ahead and substitute x equal 2 in there, and that'll give you an approximation to e squared using the summation. So if I do that, I'd have 1 plus, remember I'm plugging in 2 everywhere, so 1 plus 2 plus 2 squared over 2 factorial, 2 cubed over 3 factorial, and so on. according to my notes here, see, I think I got the right number of terms. Looks like 7.35556. Darn it. So it looks like it's good to at least one decimal place. So that's nothing more than to show that it's somewhat of a good approximation. Dang it, sorry guys. So, one thing I want to point out is that these approximations, if you only want to take a few terms, like this case we've only taken 7, which seems like a lot, but notice that x was only a small number, it was 2. And my approximation was only good to one decimal place. If I want to be more accurate, I've got to take more terms. The bigger x gets, the more terms I need to get a smaller accuracy. So one thing that we'll do here in a few minutes is we'll look at the idea of how many terms do we really need to be accurate. So I think what I did last semester was I did MacLaurin before Taylor. And that seemed, I think, to work out a little nicer. So I'm going to try that and see what you guys think. So, let me write out the function for a MacLaurin series. So a MacLaurin series is a Taylor series centered at 0, which means it's a little bit nicer to work with. So the definition is the summation from 0 to infinity, the nth derivative of f evaluated at 0 divided by n factorial all times x to the n. So the first couple terms here would be the function at 0. So when n is 0, that means the 0th derivative or the original function. And then everything else here goes to 0 or to 1, right? So we've got the original function at 0, x to the 0, that's 1, and 0 factorial by definition is 1. If I let n equal 1, I get the first derivative evaluated at 0. I get x to the first power, and on the bottom I get 1 factorial. Okay, if I let n equal 2, that's the second derivative. Evaluated at 0, x to the second power over 2 factorial. And then one more term, it's f triple prime x cubed all over 3 factorial. And this continues on. So that's just the format or the formula for a MacLaurin series. So first example says f is equal to e to the minus 5x. Says use the first 20 terms of the series to approximate e to the minus 15. Okay. Now I'm only going to write out maybe the first 4, and then I'll use a computer program to do the rest. So let's go ahead and start expanding this guy. Notice I need the function evaluated at 0 and then all the derivatives. So first I have to find those derivatives, plug in 0. So here's f of x. We need f prime. Well, we would just bring minus 5 down in front. Then we need double prime. So that would be bringing another minus 5 down would be 25 e to the minus 5x. Triple prime would be minus 125 e to the minus 5x. And we could keep going. Next, I would like the function and its derivatives evaluated at 0. So f of 0, f prime, double prime, and triple prime. If I plug 0 into this exponential, the exponential goes to 1. And then all these terms will just become their coefficients, right? Because e to the minus 5x is 1. You leave the minus 5 behind, and so on. All right. So let's write out the first 4 terms of the expansion then. So e to the minus 5x is approximately equal to the original function evaluated at 0. That's 1. Then we would do plus f prime, which is a negative 5. So this becomes minus. There's also an x and 1 factorial. F double prime is equal to 25, so plug that in. So plus 25 x squared over 2 factorial. And then triple prime, so we get minus 125 x cubed over 3 factorial. And again, that continues on. So that is to 3 decimal places, or sorry, 4 terms for that expansion. I also want to get an approximation from my calculator of e to the negative 15, because I want to demonstrate how this is going to work out. So e to the minus 15 is 3.059 02 something times 10 to to the minus 7. Okay. So let me figure out how to get my screen up here for you. And it's going to go nuts for a second there because my screen is showing you. Let's see if maybe I make this big. Nope, still doesn't want to do it. Okay, let me try doing this. By enjoying the endless picture that I just created. Just give me just a second. I'll pull up Mathematica. So I'm going to have to minimize the tab just so you can see my screen and not that craziness. If anything happens, write something in the chat for me. So an exam question for a MacLaurin series would be something like find the MacLaurin series expansion, give me the first 5 terms, use it to approximate a number. So can you guys all see my screen with Mathematica on it now? Is that a yes? No? Maybe? Give me something to work with, please. Fantastic. All right, so I want to create a MacLaurin series for e to the minus 5x. I believe the command is just series. And then I tell it start at n equals 0 and go to 20, I think, something like that. Alright, so let me check this. Okay, power series, yeah. I need to put x from 0 to 20. Okay, so that is 20 terms. And I guess 21 technically, plus this, see this O of x? That's something we don't want. So what we can do is we can say normal, and that'll truncate that right on off of there for us. Notice how it got rid of that O term. So what I wanted to do was to call this some kind of function. So I'm going to call this, let's call this A, which is a function of x. All right, and that colon just makes it so I don't have to look at all those terms. So now I want to plot A of x, and I also want to plot e to the minus 5x. It's probably going to be too big of a space. Let's try minus 2 to 2 and see how that looks. planing. Let me just try to call this A and see what it does. Okay. So I have to go past 2. Alright, so notice there are 2 curves here. One of them follows the axis, the other takes off, the blue one here. So they're both overlapping on this side, and then all of a sudden this one just kind of takes off. Now let me show you something. If I make another one called B with the same attributes, I'm just going to take less terms. Let's take 5. So I'm also going to plot B here as well. So there's the green function, that's e to the minus 5x. The blue function, which was our A, and now here's B. So what am I trying to get at here? As I said, the number of terms determines how accurate you are. If we were only to take the first 5 terms of this MacLaurin series, we could really only be accurate for values of x that are between, say, -1/2 and 1/2. Anywhere outside of that, we start to stray away quite a bit. For 20 terms, we can be accurate within the negative, maybe 1.5 side or so, but only there up to about 2. Once we get outside of 2, we're not so accurate anymore. Now, why did I do that? Well, I want to plug in to A, right? It told me to approximate e to the minus 15. Hold on a sec. So we're just deriving, then plug and play for however many terms you're looking for. Most of the time, yes, it's find derivatives, plug them in, approximate, that sort of thing. So you can't see the intersections. Oops. Come on, mouse. Darn that mouse. So they're all overlapping here. Can you see my mouse? Can you guys see the intersections now or no? Unfortunately, if I try to look to see what you're looking at, I won't be able to see it. So, okay, good. So yeah, the green one was the original function, and it travels all the way along the axis. Blue was 20 terms. This yellow here is only 5 terms. So what I was saying was the problem then said, okay, with 20 terms, please give me an approximation to e to the minus 15. Now we've already shown here in the graph, this is not going to be a very good approximation, right? Because e to the minus 15, well, that's way off our graph, and these two things for 5 terms is separating immensely. So let's see what happens. So in order for e to the minus 5x to become e to the minus 15, I need to let x equal 3. So it gives me this gigantic fraction, and let's say numerical value, 57,612. And I just got done telling you e to the minus 15 is 3.05 10 to the minus 7. So what I just wanted you to understand that it's okay that we got this crazy number. We just have to know that to be this accurate, we need a lot of terms. I want to say it was like 54 terms we needed in order for it to be accurate. So yeah, I just took 54 terms and it was 3.08 10 to the minus 7. So that's a crazy amount of terms. And we can possibly look at this. I don't know how big the number is going to be. Well, it's going to be 10 to the minus 7, so this might not be a very good idea, but let's see. I guess I want to be at x equal 3, not negative 15. Come on, man. What are you doing? So if we want accuracy out to 3, which would make it negative 15. Then these two should overlap there. And they're still pretty far off. I know why it's giving me this now. Sorry. There we go. I don't want to see that. We want our 20 terms back. Replot. There we go. Okay, so for the two equations to be close out at 3, right, it looks like 20 terms is enough, but if we really zoomed in there, they're already starting to separate. And you can see the scale here is 10 to the 7th. So that might not look like much, but if we zoomed in, it would be. So now we need 54 terms for this to be a good approximation. All right. So back to the board. So that was one example of a MacLaurin series expansion, which turns out to be a power series. So you'll often hear me say power series expansion of a function. And I would also normally try to let you guys do some of these, but because of the circumstances, I think it might be best if I just work through them. The next example has f of x equal to sine of 2x. And again, it says, give me the first 20 terms to approximate sine of 10, which means x is going to equal 5. Come on, camera. You can do it. Come on, autofocus. There we go. Jeez. All right. So we need our derivatives. So let's do that. This time I'm going to go out to the fourth derivative. So derivative of sine is cosine. Derivative of the inside brings out the 2. Next, derivative of cosine is minus the sine, bring out another 2. Another derivative brings out another 2 and makes it a cosine again. And then finally one more derivative brings out another 2 and gets us back to positive sine. We may need to go further than that. We'll see. So now I need to plug in 0. So yeah, let's go one more here. So one more derivative would give me 32 cosine 2x. So now if I plug in 0 for all of these, so f of 0, f prime, double prime, triple prime, fourth and fifth derivatives, evaluated all at 0. What do all of those give me? Well, any of them that are sine functions, right? Sine of 0 is 0. So those all get eliminated. This is 0, 0, 0. Then all of the terms that have cosines will stay. And they'll become the coefficients, right? Because cosine of 0 is 1. So I get the coefficient 2, negative 8, and 32. Now here's the biggest thing that I've seen in the past. You have to write out all of these terms when you do your expansion. If you fail to do so, what I've seen is that people will put this as their first term. It's going to be the first term that exists, that stays behind, but it's not the first term. So remember, the series is 0 to infinity, f nth derivative at 0 over n factorial times x to the n. So if I write out the first couple terms, the first term is 0 times x to the 0 over 0 factorial plus 2 times x to the first over 1 factorial plus 0 x to the second over 2 factorial minus 8x cubed over 3 factorial plus 0x to the fourth over 4 factorial, and finally plus 32 x to the fifth over 5 factorial. Hopefully you see what I'm talking about as to how you could easily get those mixed up, get the wrong x's attached to the wrong coefficients, and so forth. So let's simplify this now. So I might say something like give me the first three non-zero terms. Well, that's 0, that's 0, and that's 0. Left behind, I have 2x minus 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial. So now, let's think about this for a second. I demonstrated this for you on Mathematica. You do not have access to such things when you're going to do your test. So how in the world could I expect you to calculate 20 terms? Especially if I only ask you to write the first 3. Well, to do that, we're going to do this. We are going to rewrite this sum into a closed form. So we have to start picking out pieces that are in common in all these terms. Yes, the 0x to the n over n factorial is 0. 0 factorial is 1, x to the 0 is 1, but it's all times 0, so all goes to 0. So, notice we have x, x cubed, x to the 5th. Those are odd powers of x. How do we represent an odd number? Anybody know? So there's a generic form for an odd number. Two n plus 1, good. So this has to be some summation. In the top, I've got x to the 2n plus 1. Now, if the first term has to be to the first power, that would mean that n has to be 0. So I'm going to start with n being 0. What else do we have going on? Well, we had 1/3 5th power. We've also got, technically, 1 factorial, 3 factorial, 5 factorial. So we've got the odd number factorial in the denominator. So this is 2n plus 1 factorial. And then on top, we've got 2 to the 1st power. 8 just happens to be 2 cubed. And oh, by the way, 2 to the 5th is 32. So we've got 2 to the 1st, 3rd, and 5th. So it is also to the 2n plus 1 power. Which means I can combine these two, the x to the power and the 2 to the power, as one term. And let me put it over here. So this is going to be 2x to the 2n plus 1 over 2n plus 1 factorial. Now, why did I want to do that? Well, I'm going to ask you to approximate a number. If I say use the first 20 terms and you start at 0, you really only got to go to technically 19. And even then, you're going to lose a bunch of them. So let's just say use the first 20 values of n to approximate sine of 10. Well, this is sine of 2x. So in your calculator, you're going to plug in sine of 10, get a number for that, And then you're also going to plug in this sum. But instead of x, we're just going to replace 2x with 10. Yes, there is an alternating term, yes. So yeah, this is plus minus plus. I forgot that guy. So we also need a -1, right, or alternating term. And it's got to alternate, it's got to start as a positive. We're starting at 0, so if we just make it n, we should be fine. Right, because when n is 0, this is 1. When n is 1, this is -1. When this is 2, this is 1. So it's positive, negative, positive, negative. Is it clear to everybody what I just did? Okay, I see no. What do you mean by no? Do you not understand the negative alternating part? Or how I got from these terms to that summation over there? Okay, so the whole sum. All right, so let's try this again. If I look at all the terms that I've written out, I have to find a pattern. The pattern that I found what is this? How the summation is helpful for me is what you're confused about? Okay. So, first off, the pattern, right? This is 2, 8 is 2 cubed, 32 is 2 to the 5th. I've also got x to the 1st, x cubed, x to the 5th. And then I've got 1 factorial, 3 factorial, 5 factorial. So each one of those, this is everything to the 1st power, or 1 factorial, everything to the 3rd power with a 3 factorial, everything to the 5th power with a 5 factorial. Those are all odd numbers, and I can represent an odd number by 2n plus 1. So this is x to the 2n plus 1, 2 to the 2n plus 1, and n, or 2n plus 1 factorial. So let me demonstrate that part. If I plug in n equals 0, maybe you can see it better here. If I plug n equals 0 in, you get 2x to the 1st power. So you get just 2x. And then on the bottom you would get 1 factorial. So 2x over 1 factorial. That's our first term. Then if I plug in n equal 1, which would be the next term, 2x, this would become to the 3rd power, or 2 cubed x cubed, which is 8x cubed, all over 3 factorial for n equal 1. And then we need to include that alternating portion, because the first term is positive, then negative, then positive, and that's going to continue. So -1 to the n, because when n is 0, that's positive 1. And when this is 1, -1 to the 1st power is -1. All right, so what else we got here? You guys said we separated the x and the constant. So yeah, I did each one individually, but it turns out they're the same power, so I put them together. So I would want you to show me the terms, right? I mean, I want you to show me the derivatives, Plugging in, I want to see the terms that you get that are non-zero. I want to see what's in the box there. And then finally, I want to see an approximation. So someone said they weren't sure what good is the sum. Well, the whole point of writing it this way is so you could do it in your calculator. Right? Because you can do sine of 10 no problem if you're in radian mode. But then I want you to also use the summation to give me an approximation. So you would go into your calculator and you would create a sum that ran from 0 to 19. And you would plug in 10 to the 2n plus 1 times negative 1 to the n all over 2n plus 1 factorial. And then that'll kick out another number. So, let's see if I have those. Looks like sine of 10 is negative 0.544. That's what I have written here. And I don't appear to have the number for the summation, so I can do that with you real quick. So go ahead and try that and tell me what you get. I'm going to do it with you. So we're going to go to math, then option 10 or 0 is summation. Use your variable x is fine. Start at 0 and run to 19. Then take inside, we want to put 10 to the power 2x plus 1 times the quantity negative 1 to the power x, all divide by the quantity 2x plus 1. And then you go to math, probability, and option 4, which is factorial. I could try to show you with the camera. I can't show you question is it going to focus in or not and have enough light. Come on. So that's 10 to the 2x plus 1. I got my summation, negative 1 to the x, and then divide by 2n plus 1 factorial in parentheses. And then run that. And it's actually pretty good. I get minus 0.544. Let me make sure my other answer I had there wasn't that number and not the... So yeah, they're pretty accurate. It's all the way down to 8 decimal places. So yeah, instead of 2x, you would replace it with 10 because x is 5 in order for it to be the approximation for sine of 10. So you could give me the answers out to as many decimal places as you like. Unless, I mean, I'll probably ask you to give me, 8 decimal places or something. We okay with this one? Anybody else want to share if they're okay to move on? Guess that's a no. So those are MacLaurin series. The only difference between them and Taylor series is that instead of plugging in 0, we're going to plug in A. And instead of x to the n, it's going to be x minus a to the n. All right. So let me go ahead and do one of those for you. So as I said, the formula here is I should be doing 1 factorial, it should be 2 factorial, it should be squared, and so on. So the problem says our function is just e to the x. Find a Taylor series for a equal 3. So this would be called a expansion about a equal 3. So this one's really nice because f and all of its derivatives are the same, right? They all equal e to the x. So if I plug into the formula, each one of them evaluated at a are all going to be the same. And they're going to be e to the a. So the original is just e to the a. And in this case, that's going to be 3. So e cubed. And so if we do 3 here, e cubed. Plus, first derivative evaluated at a, that's e cubed, x minus a all over 1 factorial. And then the next one is e cubed, x minus 3 squared, all over 2 factorial. And one more would be e cubed, x minus 3 to the third, over 3 factorial, and so on. So the first problem just asks you to find the Taylor series. That's it. So let me demonstrate another one. Okay. So this time it says let cosine of x be the function. And we want to do this about a equal pi. Okay. So we've got to take a bunch of derivatives. Let's just leave it in that expanded form for the series. Yes, that is fine. Unless I say give me the closed form. We'll do that for this one. So let's take the derivatives. So first derivative cosine is minus the sine. Second derivative is minus cosine. Third derivative is going to be back to sine. And the fourth derivative can get us back to cosine. Okay. Then we need all of them evaluated at pi. So cosine of pi, that's minus 1. Sine of pi, 0. So this one down here is also 0. This one here is going to be minus a negative 1, so positive 1. And this one's going to be back to negative 1. Everybody with me so far? Okay. So now that I have all of those, I need to plug them in. So I need the function at a, that's negative 1. Then I need the first derivative at a, that's 0, times x minus a to the first over 1 factorial. Right, even though these are going to go to 0, when I write out the terms the first time, I need to include them. Then I need plus second derivative which is 1 times x minus a squared over 2 factorial. Then the next term is going to be plus 0 times x minus a cubed over 3 factorial. And then finally, a negative 1 x minus a to the 4th over 4 factorial. Right, and then we could keep going. And since a was pi, let's plug that in everywhere. So that is the first 5 terms. If I asked you for the first 3 non-zero, you'd be fine. That one's 0, that one's 0, and you're left with minus 1 plus x minus pi squared over 2 factorial. And if we really want, we could write this as 0 factorial down there. And then next term is minus x minus pi to the 4th over 4 factorial. So those are the first 3 non-zero terms. We would say plus dot dot dot. That is our Taylor expansion. Can you guys see it okay? Okay. So, what's the next part? Well, if I just said give me the first 3 terms, you'd be done. If I said give it to me in a closed form, then I would need to find a pattern and be able to rewrite that as a sum. So, what kind of pattern do we have here? Well, I see it alternates, starting with a negative. Well, we don't know what n is yet. So it's got some negative 1 to some power, right? We don't know what that power is just yet. We notice we've got 0 factorial, 2 factorial, 4 factorial. Those are all even numbers starting at 0, and an even number is represented by 2n. So if I put 2n factorial down there, then that gets me even numbers. And if I let n start at 0, right, I get 0 factorial. And when n is 1, I get 2 factorial. When n is 2, I get 4 factorial. So I'm going to let n start at 0. If n starts at 0, I need my first term to be negative, which means negative 1 to the n does not work. It needs to be negative 1 to the n plus 1. That'll make my first and third terms negative. And then finally I have an x minus pi to an even number, so I need to include that. X minus pi to the 2n. So the question is, what am I looking at here? What is this? Well, it's the Taylor expansion of cosine of x about a. So this is really an approximation to cosine x minus pi. And why did I bother doing that? Well, the next logical step is now that we can create these things, we want to be able to use them. And the question is how? Well, I'm going to tell you that the cosine of x has a common series that looks like this. So the main difference here is that we've gone from x to x minus pi. Now the fact that cosine alternates back and forth is why this is a different negative in front. But you can see that these are very closely related. So if I said, okay, here's cosine x, can you give me cosine of 2x? Yeah, no problem. Throw a 2 in there, throw a 2 right there. So that's what we're going to want to do next. So we did our Taylor series, we did our MacLaurin series. Now we want to, well, instead of shifting them like that, the first thing we're going to do is use common power series to produce a power series representation for functions that we're not familiar with or that we want to use and just don't know how to. So are there any questions about this guy? Alright, so let me go ahead and erase this guy. And then let's go ahead and take care of this next part. So the next problem in the guided notes says we've got these functions. Can you use their common power series to write them as simply a power series? So first example, I've got f of x equals x cubed times what's called cosh of x, or hyperbolic cosine. You may or may not get into that in Calc 3. You've probably never heard of cosh before. So I'm here to tell you that the cosh function has a common power series that looks like this. Pretty close to cosine, but no alternating term in there. So as we know, the whole point of MacLaurin series is to get a power series representation for something. Power series are, at their core, a polynomial. And so this x cubed is already a polynomial, right? So I'm going to leave it alone. I'm going to multiply it by this summation. Now, x cubed has no n's in it, which means it can freely go in and out of that sum. So I am going to take it inside. And when I do that, x cubed times x to the 2n, I can just add their exponents. That is the power series for the function x cubed hyperbolic cosine of x. And if you wanted, you could write out the first couple terms. So that'd be x cubed plus x to the 5th over 2 factorial plus x to the 7th over 4 factorial, and so on. All right, the next one is function x over 1 plus x. So again, x you can leave alone. What we want to do then is find a power series representation for 1 over 1 plus x. 1 over 1 plus x is equal to the sum n equals 0 to infinity, -1 to the n times x to the n. So I just plug that in. Apparently all my markers are dying on me. Again, that x can go inside. So f of x here is sum -1 to the n x to the n plus 1. So to give me an idea that you have a clue what I'm doing, tell me how I would start this guy. So I have f of x is equal to the cosine of x over x squared. So what should I be looking for in terms of a power series? Or another way to say it is, what function should I be replacing here? Okay, so I'm leaving the 1 over x squared, and I am looking for the power series of cosine. That's good. So cosine, if you look it up in your chart I gave you, should be -1 to the n, x to the 2n, over 2n factorial. So f of x then is 1 over x squared times that sum, Again, this x can go freely inside the sum. And if we have x to the 2n divided by x to the second, we can subtract their exponents. And if you prefer, you could write that as 2 times n minus 1. If you don't want to do 2n minus 2. And that then is the power series representation for that function. Now, your next question might be, well, what good is this? Well, there's going to be a case where, right, we're doing Calc 2, so eventually I'm going to ask you, integrate something. So if I say to you, integrate cosine x over x squared, you can get an okay approximation if you were to write out, say, maybe the first 5 to 7 terms of this sum and integrate those instead. Well, right now it looks kind of ugly, but when I write out the couple terms, I just get a polynomial. And we all know polynomials are really nice to integrate. So question, you said this stuff comes back in Calc 3 diffie q. What would you use these series in other than Calc 2? So in diffie q, there is a method of solving differential equations using a series solution. And at the end of that, you end up getting a bunch of terms, and so you end up wanting to write your answer as one of these guys. So you may not be finding a Taylor or MacLaurin series, but at least the skill of taking a bunch of terms and turning it into a summation is something that you would certainly need in that class. So something I would like you guys to do is, so this says the applications of series, right, for the next set of stuff. I would like you to do the first problem in that section before next class. So it asks you to find the first 3 terms, first 6, first 10, approximate the number in your calculator, and then also figure it out with the certain number of terms that you found, and then it asks you to discuss something about it. So what I'd like you to do is, if you can, do that, and maybe you could probably use Desmos, which is an online graphing utility. They have a lot of other stuff, but it can graph pretty well. So what I'd like you to do is maybe graph your 3, 6, and 10 terms versus sine of x, and just see how close they are. And then we'll do that again at the beginning of next class. So I think I want to do maybe one of these integrals, and then we can call it a day, and then we can finish up the rest of this stuff next time. And next time is actually review, because we've finished everything that we need for the next exam. I don't know about you guys, but it feels like since switching to doing this all at home, it seems like these exams and things come up so much faster than they used to. Kind of sneak up on you. Alrighty. So as I said, let me do one more of these problems. So it says here to approximate a definite integral. It says use the first 6 terms of the series. So the integral here is from 0 to 0.4. And it is 1 over 1 plus x to the 4th dx. And we're told that f of x is 1 over 1 plus x, and its approximation is the sum from n equals 0 to infinity, negative 1 to the n, x to the n. So with the last set of stuff, we had things where we had to multiply into the sum. This time we want to replace, right? We've got x here, and I need to replace it with x to the 4th in order to get the sum that I want. So 1 over 1 plus x to the 4th is approximately the sum of negative 1 to the n, x to the 4n. Because instead I plugged in x to the 4th instead of x. All right. So let's write out the first couple terms. It says use the first 6. So when n is 0, this is negative 1 to the 0, x to the 0, plus, then we get negative 1 to the 1st, x to the 4th, negative 1 to the 2nd, x to the 8th, negative 1 cubed, x to the 12th, negative 1 to the 4th, x to the 16th. Right, I'm just plugging in n equal 4 for each one of these, or n equal 0, 1, 2, 3, 4. And then finally negative 1 to the 5th, x to the 20th. Whew, okay. That simplifies to 1 minus x to the 4th plus x to the 8th minus x to the 12th plus x to the 16th and minus x to the 20th. So that is a 6-term approximation to that function. So when I ask you to approximate the function using the power series, keywords there, you just plug in that power series and integrate. And again, we all love this because integrating polynomials is easy, right? This is x minus x to the 5th over 5 plus x to the 9th over 9, and so on. All evaluated from 0 to 0.4. So in all reality, we just got to plug in 0.4 everywhere, because if we were to plug in 0, every single one of these terms would go to 0. Plugging in 0.4 and doing all the work, you get 0.397951. for the approximation. If I plug this into Mathematica or your calculator, for instance, right, the FNINT function, it tells me 0.39791. Not so bad. So these good to 4 decimal places, and we only used 6 terms. But again, realize, right, we had very small values of x, 0 and 0.4. So the next problem is almost exactly the same thing. So maybe go ahead and give that one a try as well. So we will finish this packet, which is very small, next time. Right, the limits only take us a very short amount of time. So I have one more integral, the problem at the beginning, but I would like you to have that done already. And evaluating limits, and then we'll spend the rest of time. You guys can ask any questions about what the test is going to look like, you know, stuff you didn't understand. I'm going to go ahead and